Determining ratios using the Pythagoras Theorem. Welcome, everyone. Let's begin our lesson on determining ratios using the Pythagoras Theorem. Now, if you look at the first slide, I want to start by reflecting on what we have already covered. In our previous lessons, we learned how to calculate trigonometric ratios quite easily, provided that the lengths of all three sides of a right-angled triangle were already known to us. However, as we move into more advanced mathematical problems, you will notice a shift in difficulty. You won't always be handed all three side lengths. Instead, you might be given only a single trigonometric ratio and then be asked to find the remaining 5. This can feel a bit tricky at first, but don't worry. To solve these types of problems, we are going to use a powerful strategy. We are going to combine our existing knowledge of trigonometric definitions with the Pythagoras Theorem. This theorem will act as our bridge, allowing us to find that missing third side so we can complete the set of all ratios. Let's move on to the next slide to understand the fundamental concept behind this approach. The fundamental concept. It is crucial to understand that a trigonometric ratio represents a proportion between two sides of a triangle, rather than their absolute, fixed lengths. To illustrate this, let's look at an example. If we say that sine of angle A equals 3/5, it does not necessarily mean that the opposite side is exactly 3 centimeters and the hypotenuse is exactly 5 centimeters. What it actually tells us is that the ratio of the opposite side to the hypotenuse is 3:5. The triangle could be much larger or much smaller, but that relationship between the sides remains constant. To handle this mathematically and avoid any confusion, we introduce a positive constant, which we'll call k, to act as a scaling factor. By doing this, we can represent our sides as multiples of k. This allows us to account for any possible size of the triangle, while ensuring that the underlying ratio remains exactly the same. This concept of using k is what we will apply in the step-by-step procedure in the next slide. Now that we've introduced our topic, let's dive into the fundamental concept that makes this entire method work. Step-by-step procedure. Now that we understand that a trigonometric ratio is a proportion and not just fixed lengths, let's look at the actual strategy you'll use to solve these problems. To find all the remaining trigonometric ratios when you are only given one, you can follow these 3 manageable steps. First, step 1. Express the known ratio as a fraction of sides. Your first task is to identify which 2 sides are involved in the ratio you've been given. Once you've identified them, we assign these sides values in terms of a constant, which we call k. For example, if you're given that tangent of a equals x/y, you would let the opposite side be x times k, and the adjacent side be y times k. This keeps our ratio mathematically accurate, as we discussed in the previous slide. Next, we move to step 2. Use the Pythagoras Theorem to find the third side. As you know, the Pythagoras Theorem states that in a right-angled triangle, the hypotenuse squared equals the opposite side squared plus the adjacent side squared. You will take the values we assigned in terms of k from step 1 and substitute them into this formula. This allows you to solve for that missing third side, also expressed in terms of k. Finally, we reach step 3. Apply the definitions of the other ratios. Now that you have expressions for all 3 sides, the opposite, the adjacent, and the hypotenuse, all in terms of k, you can write out the other 5 trigonometric ratios. The beauty of this method is that when you perform the division, the constant k will simply cancel out, leaving you with the final numerical ratio. In the next slide, we are going to see this exact process in action with a real-world example involving a ladder. Real-world application example. Imagine a technician leaning a ladder against a vertical wall. We are told that the angle, theta, which the ladder makes with the ground, results in a sine of theta equal to 8/17. To ensure the ladder is stable and reaches the correct height, the technician needs to find the remaining trigonometric ratios. Now that we have understood the theory and the 3-step procedure, let's put everything into practice with a real-world application. Let's walk through the solution together using the steps we just discussed. In step 1, we express the known ratio as sides. We start with the definition of sine theta, which is the opposite side divided by the hypotenuse. Since we are given that sine theta equals 8/17, we apply that scaling factor, k, that we talked about in the previous slide. So, we will let the opposite side, which represents the height of the wall, be 8k, and the hypotenuse, or the length of the ladder, be 17k. Next, moving to step 2, we need to find the third side using the Pythagoras Theorem. Our goal here is to find the adjacent side, which is the distance from the base of the wall to the foot of the ladder. We use the formula, hypotenuse squared equals opposite squared plus adjacent squared. Substituting our values, we get 17k squared, which equals 8k squared plus adjacent squared. When we square the terms, we get 289k squared equals 64k squared plus adjacent squared. To isolate the adjacent side, we subtract 64k squared from both sides, leaving us with adjacent squared equals 225k squared. No direct match, part of the calculation flow. Finally, by taking the square root of both sides, we find that the adjacent side is 15k. Now, for step 3, we can determine all the remaining ratios. We now have all three sides. The opposite is 8k, the adjacent is 15k, and the hypotenuse is 17k. First, cosine theta is adjacent over hypotenuse, which is 15k over 17k. Notice how the k cancels out, leaving us with 15 over 17. Second, tangent theta is opposite over adjacent, which is 8k over 15k, simplifying to 8 over 15. Third, cosecant theta is the reciprocal of sine, so it becomes 17 over 8. Fourth, secant theta is the reciprocal of cosine, giving us 17 over 15. And finally, cotangent theta is the reciprocal of tangent, which results in 15 over 8. As you can see, once we found that third side, all the other ratios fell into place perfectly. However, as we will see in the next slide, there are a few common pitfalls to watch out for when performing these calculations. Common mistakes to avoid. Now, before we wrap up and look at our final summary, I want to pause and discuss some common pitfalls. Even if you understand the concept, it is very easy to lose marks on these specific errors, so please pay close attention. First, let's talk about ignoring the constant k. When you are working through a problem, you might be tempted to simply assume the sides are exactly the numbers you see in the ratio, for instance, using 8 and 17 directly from our previous example. Now, while this shortcut might lead you to the correct final numerical answer, it is mathematically incomplete. Remember what we discussed in slide 2. A ratio describes a relationship, not a fixed length. To be mathematically rigorous and formally correct, you must use the constant k to represent these sides as multiples. Second, watch out for incorrect side identification. This is a fundamental error that can ruin your entire calculation. You must be absolutely certain you have correctly identified which side is the hypotenuse. Always remember the golden rule. The hypotenuse is always the longest side of the triangle, and it is always positioned directly opposite the 90-degree angle. Finally, be very careful with calculation errors when applying the Pythagoras Theorem. A very common mistake I see is adding the square of one side to the square of the hypotenuse, instead of subtracting. If you are trying to find a missing leg, such as the adjacent side, you must subtract the square of the opposite side from the square of the hypotenuse. To be clear, the correct way is adjacent squared equals hypotenuse squared minus opposite squared. The incorrect way, which you must avoid, is adjacent squared equals hypotenuse squared plus opposite squared. Keep these 3 points in mind, and you will avoid the most frequent mistakes students make in this topic. Key takeaways. First, always remember that a ratio is not the same as a fixed length. As we discussed in our fundamental concept slide, a trigonometric ratio is simply a proportion. To keep your work mathematically rigorous and avoid the common mistake of assuming fixed values, always use that constant, k, to represent your side lengths. Second, think of the Pythagoras Theorem as your bridge. This is the most critical part of the process. It is the tool that allows you to move from knowing only two sides, which is all a single ratio provides, to knowing all three sides of the triangle. Without this bridge, you'd be stuck with incomplete information. Third, focus on consistency. Once you have successfully expressed all three sides, the opposite, the adjacent, and the hypotenuse in terms of our constant, k, finding the remaining 5 trigonometric ratios becomes a simple matter of substitution and division. As you saw in our latter example, the k will eventually cancel out, leaving you with the final numerical answers. Finally, let's quickly recap the formulas you should have memorized. To find the hypotenuse, take the square root of opposite squared plus adjacent squared. To find the opposite side, take the square root of hypotenuse squared minus adjacent squared. And to find the adjacent side, take the square root of hypotenuse squared minus opposite squared. To wrap everything up, let's review the key takeaways from today's lesson so you can approach these problems with confidence. Keep these formulas handy, and you'll be able to solve any problem of this type. Great job today!